All right, hello everyone. So what we'd like to do now is kind of shift gears in the course, and we're going to start talking about rotational motion, which is really interesting. So far we've talked really just about translational motion. So here we have an object. This is an extended object as opposed to a point particle. So it has length, width, and height and so on. And it's a special kind of extended object called a rigid body. Okay, so it doesn't change its shape. Now, we've talked about translational motion of objects. Okay, so this object here, it can have, displacements or velocities or accelerations in, say, the x direction, the y direction, the z direction, or generally it can be moving on some arbitrary trajectory in three-dimensional space like this under the action of a net force causing an acceleration and so on and so forth, okay? But we haven't talked about rotational motion. Okay, so for instance, when we talk about blocks on inclined planes, well, the block is always sitting like this on the inclined plane. We let it go, it accelerates in that direction. There's a translational acceleration in that direction, but we always ignore, or we always consider cases where there's no rotation as well. Okay, so it's not rotating. But of course, in reality, if I just take this block of wood and I throw it up in the air, well, the center of mass is going to move along a parabolic trajectory like this. But on top of that translational motion of the center of mass, this object could be rotating like this. It could be tumbling like this. Okay? And so introducing or considering the rotational motions of objects in addition to their translational motion adds an entirely new dimension and richness to how objects can move. Okay, so so for instance, this object can be rotating about its center of mass point around an axis in this direction, so like this. It could also be rotating about its center of mass around an axis in this direction. It could also be rotating about its center of mass around an axis in this direction, okay? So in general, it can be doing some really, really complicated kind of motion like this. And not only that, X, Y, Z rotation, direction of rotations. Not only that, it could be rotating not about, say, the center of mass, but about the end. Right, so I could make this rigid body rotate about this point around an axis that's in this direction. So I could make it go like this. Okay, so there's all kinds of really, really complicated sorts of rotational motions that we can consider, and they're all really interesting. Okay, so so the challenge here is that we are much more familiar with translational motion. So we know, in order to make this shopping cart, accelerate in this direction along the x-axis, I need to exert, pick up speed faster and faster and faster. I need to exert a force in that direction along the x-axis to make it have translational motion faster and faster along the x-axis. But what if I want to take this object and I want to not make it translate, but make it rotate faster and faster and faster? It starts out with no rotation, and then it starts rotating faster and faster and faster. Well, how do I do that? I can't exert a translational force like that. I have to exert a different kind of force, an entirely different kind of force, like a twisting force, okay, which is called a torque. Okay, so, and we're not as familiar with twisting forces as we are with, linear or translational forces. So that's one thing, is it intuitively it's richer. Okay, it gives you a chance to build your intuition in more interesting directions. But also it's mathematically more complex. So torque, for instance, involves the cross product of two vectors, the vector cross product. So we'll be talking more about that. But the idea is, you have a vector in this direction in three-dimensional space, another vector in that direction in three-dimensional space. The two of them together define a plane, and then the cross product of those two vectors is perpendicular to that plane. So we're always drawing sort of one vector, another vector, and then a third vector perpendicular. So we're always drawing things in three-dimensional space. Okay, so either sort of like face on, and so the third vector is coming out of the page, or we're drawing it within some perspective, and we really need to draw in 3 dimensions like perspective and stuff. So, it really challenges your three-dimensional thinking. Okay, so anyway, so it's rotational motion is a lot of fun. We've spent about 2/3 of the course sort of reviewing translational motion, which most of you have seen in high school already. We've sort of upped the level of the conceptual depth and mathematical depth. Now we're going to spend the last third of the course talking about rotational motion. So there's rotational kinematics, dynamics. There's a rotational kind of momentum called angular momentum. There's conservation of angular momentum, just like there's conservation of linear momentum, and so on. So it's a very, very rich and interesting topic. All right, very good. So let's get going on that. So what we're going to imagine is we're going to just draw a generic sort of rigid body like this of some sort of arbitrary shape. So this is a generic rigid body here. And the idea is we're going to rotate this object. Okay, so the first question we need to ask is, well, about what axis are we rotating it? Okay, so let's suppose that we take a what's called a pivot point over here. Say just pick any point over here, and we could rotate this object, you know, say in this direction about that pivot point, or in this direction about that pivot point, and so on. What we're going to imagine is we're going to rotate this object with this point fixed about an axis that's perpendicular to the plane of the page here. So it'll be like this. It'll be like this as opposed to, say, like this. Okay, so we're going to be doing that. So the axis of rotation passes through the pivot point over here, and the axis of rotation in this very simple example is just perpendicular to the page. Okay, great. So now we're going to rotate this. Now we're going to rotate it through some angle. Okay, so we need to be able to describe, well, what is the angle? So we're going to change the angular position of this object. It has some angle now, and then later on it'll have a different angle. It will have changed its angle. So the first question is, well, what is the angular position of the object now? Well, the way to define that is to make it concrete, is just to pick an arbitrary point, doesn't matter what point you pick, that's in the rigid body, okay? And let's pick that point over here. And let's suppose that that point is located a perpendicular distance r away from the axis of rotation. So we're going to be doing a lot of this sort of thing. So here's a point, and here's an axis of rotation. What is the perpendicular distance from this point to the axis of rotation, which is basically the minimum distance? Okay, so it's the line of shortest length to get from this point to this axis of rotation. If you go way over there, it's longer, way over there, it's longer. The perpendicular distance from the axis of rotation to the point in question is the shortest distance. Okay, we'll call that point P. Great. So now we say, well, what is the angle of this object, the angular position of this rigid body? Well, we'll take it by definition to be the angular position of that point P. Well, relative to what? All positions are relative to something. So we'll take the horizontal, by convention, the horizontal axis here. We'll call that the angular position theta equals 0. So if this point P is located on theta equals 0 axis, then the angular position of the object is 0. Okay, but this object is already not at 0. It has an initial angular displacement, angular position, theta initial. Okay? And now what we're going to do is we're going to rotate this object, and always sort of in the back of our mind is we're changing things, and that change is happening in a certain time interval. You know, delta t is from t initial to t final is t final minus t initial. So we're going to rotate this rigid body like this through some angle. So it'll start looking like this, and then it'll end up looking something like this. Okay, so we've rotated it like this. So the point P has moved through an arc of a circle to that point over there. Okay, and so the initial angular position of the rigid body was theta initial, and then the body rotated to a new angular position, which we'll call theta final. Okay, and so the change in the angular position, or the angular displacement, is delta theta, theta final minus theta initial. So we will define the angular displacement is defined to be, delta theta is the change in the angular position. So that's theta final minus theta initial. And that's measured in radians. Okay, so it was initially, so pi over 2 is here, is maybe like, pi over 4, and then it went to, or whatever, a little bit more than pi over 2. Okay, so there's been a change in the angular position, theta final minus theta initial. Now, just like changes in linear position can be positive if you're moving to the right, or negative if you're moving to the left, this delta theta can also be positive or negative. Okay, and so delta theta, the angular displacement, will be positive so greater than 0 for counterclockwise rotation. So starting here, ending here, so theta final is bigger than theta initial, and so delta theta, the angular displacement, is positive, and that happens for counterclockwise. Counterclockwise is always positive, okay, for mathematicians and for physicists, okay, usually. Sometimes it's more convenient to define this direction to be positive, depending on the situation. But anyways, in this setup here, we've said, okay, counterclockwise is positive. So then if the object rotates this way, then theta final will be less than theta initial, so delta theta will be negative. Okay, and so that's for clockwise rotation. Okay, great. So that's the angular displacement. It's the change in the angular position. Okay, but now there's something very important. There's a different kind of displacement. When we're talking about rotational motion, there's angular displacement and there's also tangential displacement. So what does that mean? Well, what it means is if you take this point P, as this object rotates around like this, the point P moves through an actual physical distance, a certain number of meters, 1 meter, 2 meter, 3 meter, 4 meter, 5 meter, 6 meter, like that. Okay? And so what we want to do is we want to define a tangential displacement, which is the actual number of meters that point P moves along. So it's the arc length of that little bit of a circle, of that fraction of a circle. Okay, and so how do we define that? Well, we take this, because this point P, as this rigid body rotates through that pivot point around this axis, okay, that point P is describing a circular motion like this. And so we'll complete the circle back to here. And we'll define this axis also to be s equals 0. So that's the tangential displacement equal to 0 here. Okay, and then the initial tangential displacement is 1 meter, 2 meter, 3 meter, 4 meter, 5 meter. So this is s initial. And then it moves from that 5 meters to 6, 7, 8, 9, 10, 11 meters. So this is s final. So it's the actual arc length along the circle. Okay, and so we define also it's really useful to define also a tangential displacement. And that tangential displacement is called delta S. And so it's S final minus S initial. And delta S is actually the number of meters. The tangential displacement is measured in meters. Okay, and so how do we define that? Well, what we need to know is what is the arc length. If we move through some angle delta theta, what is that arc length? So this is a super important and simple mathematical identity that you should know. So if we have, say, a wedge of a circle, part of a circle here, and we say, yeah, that wedge opens up with a certain angle, say delta theta, okay, then so that's the angular displacement of this line. Okay, but what is the actual physical distance that you need to move? Well, if this point is a radial distance r away from the axis of rotation here, then that arc length, delta s, will clearly be proportional to r. That's the important thing to understand. Because if I take, if my arc of a circle is a radial distance r away from the axis of rotation, if I double r from here to here, then the tangential displacement will also double. It's just like similar triangles, right? We've doubled the side length of one, and so we've also doubled that length. And so delta S is certainly proportional to R. The further you are out, the greater will be your tangential displacement. Delta S is proportional to R, and that proportionality factor is the angle, the opening angle delta theta. And you can see that that's obviously right, because if we take our angular displacement to be 2 pi, which means we've gone all the way around the circle, then delta theta is 2 pi, and we have 2 pi r on the right-hand side. Well, that's just the circumference of the circle, and that really is the actual distance that you move around that circle, the number of meters that you move around that circle. Okay, so this is a super important relationship. So a lot of what we do in rotational motion relies on understanding this. Okay, so sort of, make sure you've mastered that concept. Okay, so, another really important thing to say here is that angular displacement is the same for all points on a rigid body. So if we say we're at this point over here and we rotate, say, through 30 degrees, the whole object rotates through 30 degrees. Every single point in that rigid body also rotates through 30 degrees. Moves from here to here, that's 30 degrees. Moves from here to here, that's 30 degrees. So they're all the same. So the angular displacement of every point on a rigid body is the same. Okay? Whereas the tangential displacement is not the same. Very important. So if you are located very close to the axis of rotation, the tangential displacement is very small, 1 meter. If your point P is located far away from the axis of rotation, then your tangential displacement is much larger. Your tangential displacement grows with the radial distance. Here it's small, here it's larger, and so on. So the angular displacement delta S, the tangential displacement delta S is equal to R times delta theta. Delta theta is the same for all points on a rigid body, but delta S depends upon how far your radial distance from the axis of rotation. The bigger R is, the bigger your tangential displacement. Okay? So that's really important to understand. Okay. So now what we're going to do is we're going to say this time interval delta t here, we've imagined to be a finite time interval. Now we're going to take the limit that delta t shrinks to become very small and becomes a differential dt in the calculus sense. So we're going to now imagine that delta t shrinks to an infinitesimal time interval, and so the object has rotated through a very small angle in that very small amount of time dt. Okay, so so then the angular displacement delta theta will also become infinitesimal, and it'll be a differential d theta. And at the same time, the tangential displacement, not equal, delta theta here becomes very small in the limit, it becomes a d theta, a differential, and delta S, a finite tangential displacement, becomes just an infinitesimal tangential displacement. So delta S becomes an infinitesimal displacement ds. Okay? So then we can start talking about instantaneous angular velocities and instantaneous angular accelerations. Okay? So we will have an angular velocity. Let me write that a little bit lower. Okay, so we will define an angular velocity. And the angular velocity is given a special name. It's given the name omega. So just like linear velocity, Vx is dx dt, it's the rate of change of the linear position. The angular velocity is the rate of change of the angular position. So omega is d theta dt. Okay, so it's the rate at which that angular position is changing. So if it's rotating rapidly, it'll be rotating at a large number of radians per second. So in 1 second, the angular displacement will be a large number of radians. So this is measured in radians per second. Okay, and that angular velocity, number of radians per second, can be positive or negative. Okay, so it will be positive or greater than 0 for counterclockwise rotation. So if the angular, if the position is increasing, if the angular position is increasing, then d theta dt is positive, and we are rotating counterclockwise. Okay, if the angular position theta is decreasing, well then d theta dt is negative, and the angular velocity is negative, and that corresponds to clockwise rotation. Okay, so you have, say, for linear motion, if the velocity is positive, you're moving to the right. If the velocity is negative, you're moving to the left. If the angular velocity is positive, it's rotating counterclockwise. If the angular velocity is negative, you're rotating clockwise. Okay, now associated with this angular velocity, there is also a tangential velocity. So for angular quantities, or sorry, for rotational quantities, there's always an angular and a tangential. Angular and tangential displacement, angular and tangential velocity, angular and tangential acceleration. Okay, so we have a tangential velocity. A tangential velocity, so what does that mean? Well, it means that as this object is rotating around with a certain angular velocity, so and so many radians per second, this point P, located at a radial distance r from the axis of rotation, will be physically moving a certain number of meters per second. So if it takes 1 second to go from there to there, it's 1, 2, 3, 4, 5, 6 meters per second is the tangential velocity of that point P. So the tangential velocity is equal to, we'll call it v subscript t for tangential velocity. So it's defined to be the rate of change, the rate at which the tangential position is changing. Okay, so the actual distance arc along the arc length of that circle. So Vt is the rate of change of the tangential position of the point P. And so ds becomes r d theta. So that's r times d theta dt. And d theta dt is the rate at which the angular position is changing, is radians per second. How fast is it rotating, radians per second? And so that's omega. So that's r times omega. So that's very important. Tangential velocity is angular velocity times r. So that the dimensions of omega are radians per second. Radians is dimensionless. Times an r, which has dimensions of meters, it becomes meters per second. So this is meters per second. Okay, so tangential velocity is the actual physical number of meters per second that that point is moving at. Now remember, it's very important that if this object has some angular velocity, say 2 pi radians per second, it's rotating around once every second. Every single point in that rigid body is rotating with exactly the same angular velocity. They all of the points move through 2 pi radians in 1 second. However, they will all have different tangential velocities. If you are close to the axis of rotation, then your tangential velocity will be small. You'll do only, say, 1 meter in a second. Here you'll do 1, 2, 3, 4, 5, 6 meters in a second. Okay, and so you're moving faster in terms of meters per second if you're further away from the axis of rotation. So the tangential velocity is the angular velocity times r. The bigger r is, the faster you're actually physically moving in meters per second. Okay, so that's very important to distinguish between tangential quantities and angular quantities. Tangential velocity and angular velocity, and tangential displacement and angular displacement. Okay. And then the third thing will be acceleration. Okay, so we will define an angular acceleration. So the angular acceleration gets a special symbol, alpha, the Greek letter alpha, and alpha is the rate of change of the angular velocity. So we have a certain angular velocity in radians per second. It's the rate at which that's changing. So it's d omega dt, and it's measured in radians per second, or radians per second squared. It's initially rotating at 5 radians per second, and then in 1 second it changes to 6 radians per second. And so the angular acceleration is measured in radians per second. Okay? And so this angular acceleration, so now this is interesting. This angular acceleration can be positive or negative in different situations. So there's actually 4 situations to think about here. So it can be positive in 2 situations, and it can be negative in 2 situations. Okay, so let's take the first situation. Let's suppose that the angular velocity is positive. So we have an object that at some instant of time has positive angular velocity, so it's rotating in the counterclockwise direction. And suppose that the angular speed, okay, the magnitude of the angular velocity is increasing. So it's rotating counterclockwise, but it's rotating faster and faster in the counterclockwise direction. Then the angular acceleration will be positive. So if omega is initially positive and the magnitude of the angular velocity, the angular speed, is increasing. Okay, so an upwards arrow indicates increasing. But the angular acceleration can also be positive if you start with the angular velocity negative. Okay, so the object is initially rotating, say, really fast in the clockwise or negative direction, but it's slowing down. Okay, then the angular acceleration is actually that way, so it's in the clockwise positive direction. Okay, so if the angular velocity is negative, but the angular speed, the magnitude of the angular velocity, is decreasing. So down arrow. Okay. Now the angular acceleration can also be negative. Okay, so let's suppose that the angular velocity is initially positive. Okay, so we are rotating counterclockwise like this. Okay, but suppose that we are rotating counterclockwise really fast, but then we're slowing down. That means that the angular acceleration is that way, as clockwise is negative. So if the magnitude of the angular velocity, the angular speed, is decreasing. It's initially some large positive amount, but it's decreasing. Okay? Or the fourth possible case is we are starting in the case where omega is negative. Okay, so we're rotating clockwise like this, slowly, but then we rotate faster and faster clockwise, which means the angular speed is increasing. Okay, so in that case, the angular acceleration is also clockwise is also negative. So the angular speed, or the magnitude of the angular velocity, is increasing. Angular velocity is negative, but the speed is increasing. Okay, so those are the 4 different cases. So make sure that you sort of like go through these in your mind and make sure that that sort of thing makes sense. Exactly the same situation happens for translational motion, say along the x-axis. We've talked about that before. Okay, and then the final thing is, yes, there's an angular acceleration, but now there's also a tangential acceleration. Tangential acceleration. Okay, and so the tangential acceleration is given the symbol acceleration A, subscript t, like velocity tangential, acceleration tangential. And the tangential acceleration is the rate at which the tangential velocity is changing. So as this object is rotating around, it could be picking up angular speed, moving faster and faster and faster. So the actual velocity of this point P along this circular arc is actually changing. And so the tangential acceleration is the time rate of change of the angular velocity. Okay. Now the tangential velocity is the constant r times omega. So its time derivative, that is the time derivative of this, will be r times the time derivative of omega. Okay. So the tangential acceleration is r times the time rate of change of the angular velocity. Time rate of change of the angular velocity is the angular acceleration. So this is equal to r times alpha. And the dimensions for this, alpha has the dimensions radians per second squared, so that's dimensionless divided by second squared, times r, okay, which has the units of meters. So this is meters per second squared. Exactly like an acceleration of an object along the x-axis. Okay, so its meters per second velocity is changing, well, it's changing at a certain rate, meters per second squared. In the same way, if this object is rotating counterclockwise, but rotating faster and faster and faster, then the tangential velocity in meters per second will be changing every second. So it's meters per second, meters per second squared. Exactly the same thing. So what's really important here is to remember that, well, I guess for the acceleration here again, so the angular acceleration of every single point on a rigid body is the same, but the tangential acceleration of every point on a rigid body is not the same. It depends upon how far you are away from the axis of rotation. Okay, so for a given angular acceleration, if you're located close to the axis of rotation, then the change in the angular velocity, meters per second, will be small. But if you're located far away, then the change in the angular velocity, meters per second, a tangential velocity, meters per second squared, will be larger. So it's proportional to r. Okay, so this factor of r is really important here. It's really important here, and it's really important here. It's the factor of r that allows you to translate between angular quantities, angular displacement, angular velocity, angular acceleration, to tangential quantities, tangential displacement, tangential velocity, tangential acceleration. You take the angular quantity and you multiply by r. So instead of dealing with radians, you're dealing with meters. Instead of dealing with radians per second, you're dealing with meters per second. Instead of dealing with radians per second squared, you're dealing with meters per second squared. So it's very important that you sort of wrap your mind around this distinction between angular and tangential quantities in rotational motion. It's really sort of central to understanding a lot of stuff. Okay, so very good. So that's sort of a bit of an introduction to the terminology that we use with rotational motion. Now let me sort of end off with a really simple example. Okay, so let me just get rid of a little bit of this stuff here, make a little bit of room for a little example. Okay, and so we're going to be looking at the Earth. We're going to be thinking of the Earth as this great big rigid body, which is rotating. Okay, and so the Earth is this big ball of rock, and it is rotating about an axis which passes through the North and South Pole. So the axis of rotation, and it's rotating with a certain angular velocity omega. So every single point in the Earth and on the surface of the Earth is rotating through the same number of radians per second. And what is that? What is the angular velocity of the Earth? Well, the angular velocity omega is, just think about how many radians it takes to, how much time it takes to go all the way around. So then every single point on that rigid body, the Earth will have rotated through 2 pi radians in how much time? Well, 24 hours. So the angular velocity, the number of radians per second that every single point in and on the Earth rotates through, is 2 pi radians divided by t, the time it takes for the period of that rotational motion, the time it takes the Earth to go around once, which is 24 hours. So if you take 2 pi divided by 24 hours converted to seconds, what you get is omega is equal to, what does it turn out to be? 7.27 times 10 to the minus 5 radians per second. Okay, so that's very good. So every single point in and on the surface of the Earth rotates with an angular velocity of 7 times 10 to the minus 5 radians per second. So that's pretty slow, right? It takes the Earth 24 hours to come around. So it's a pretty slow rotation. So now what we're interested in is, so that's the angular velocity. What is the tangential velocity? Well, tangential velocity of what? We need to specify how far away is it? What is the perpendicular distance of that point from the axis of rotation? So the simplest example is to consider a point on the equator of the Earth. So here's the equator of the Earth. Let's take a point on the equator of the Earth. That's our point P here. Okay? And so that point P is located what perpendicular distance away from the axis of rotation? Well, in this case, R here is just the radius of the Earth. Okay? And so then we can ask, well, what is the tangential velocity? With what meters per second is a person standing on the equator moving at? So what is that tangential velocity Vt? So we can work that out. The tangential velocity Vt is equal to, we convert angular velocity to tangential velocity by multiplying by r, the perpendicular radial distance from the axis of rotation. So that's just r times omega. So we take the radius of the Earth, which is 6,340 kilometers, convert that to meters, multiply this by the omega radians per second, we'll get meters per second. And that turns out to be 461 meters per second. Okay, so someone standing at the equator is moving at 461 meters per second. Okay, and so that's the speed of sound is like a 330, so they're moving at faster than the speed of sound. Okay, now of course, this tangential velocity depends upon the perpendicular distance away from the axis of rotation. So if we take someone, say, living up here in Canada, okay, so that's like up here, then the perpendicular distance to the axis of rotation is now less. Their angular velocity is the same. They still complete 2 pi radians in 24 hours. However, they are located closer to the axis of rotation, and so their tangential speed is less. And if you go like right next to the North Pole there, well then your tangential velocity is extremely slow. Because if you have a 1 meter circle, it takes like 1 meter in 24 hours. It's very, very slow compared to this 461 meters per second. Okay, so that's a sort of a good example. And is there a tangential acceleration? Well, there would be a tangential acceleration if the tangential velocity were changing. So if that would happen if omega was changing. Now, it's true that omega is changing. Omega is decreasing, okay, with time. So the angular velocity of the Earth is slowly decreasing due to the effect of tides and stuff like that, and friction in the oceans and this and that. So it is slowly decreasing. So there is a very, very small angular acceleration, which is negative. So the angular velocity is slowly reducing. And so there's a very, very small tangential acceleration, okay, in the direction backwards like this. Backwards to the tangential velocity. Okay, but that's very, very small. So in the case of the Earth, the tangential acceleration is approximately 0. But now you'll notice that we are actually dealing with circular motion here. So we have a person moving around in a circle of radius r equal to the radius of the Earth, and with a tangential speed of 461 meters per second. So we could ask the question, what is the centripetal acceleration? So the acceleration towards the center of the circle. And so centripetal acceleration is v squared divided by r. In this case, it's the tangential velocity squared divided by the radius of the Earth. So if you put 461 meters per second squared divided by the radius of the Earth, you get 335 meters per second squared. And so that's an acceleration, so you want to compare that to g. So g, free fall acceleration at the surface of the Earth under gravity, is about 10. So this is about 0.3 times g. 0.3% of g. So less than a third of a percent of free fall acceleration. Okay, so to the extent that this is small, okay, compared to the accelerations we have near the surface of the Earth, a reference frame attached to the surface of the Earth is, approximately an inertial reference frame. Okay, so very good. So this is a very, very simple example of the difference between, angular velocity and tangential velocity and so on. It's that factor of r that's really important to wrap your mind around. Okay, so very good. So this is a bit of an introduction to the terminology that we use with rotational motion. So try to master that terminology, and we'll turn our attention now to rotational kinematics.